Welcome to the 2020 AP Physics 1 review. This is the second video. You should be going in order. If you know the previous material, that's fine. You can just go a little bit faster, but definitely try to go in order of the videos. So the last video, I discussed Unit 2, Systems, Gravitational Field, and Contact Forces, including free body diagrams. Before we continue, it's always good to have a review. The review indicates whether you understand the information, and there's nothing more important in physics than understanding the previous information. That's where I see the biggest breakdown in knowledge, is that a student may skim over previous information, and then that hinders them from learning the next part, because there's no other subject like physics where it's all dependent on core principles from the very beginning. To that end, I designed some review questions. So you should definitely pause the video and try to answer these, because you shouldn't go forward without knowing these answers. Now, I know you're going to go, well, is my answer right or wrong? Well, you could definitely look back at the previous video. But if you look at the way I did the questions, you're going to notice something that they're going to do on the AP Physics exam. I put them in different orders. So what I did is I put the questions that go towards the end of the video in the beginning, and I mixed them all up, because there's almost no way that they can prevent anybody from looking at other material because of all the different ways that you can do it. So how are they going to make it more fair to everybody? Well, they're going to mix up the materials so that you can't look in one place to get everything. And think about it. If you're watching that last video was a half an hour. If you're watching that video, the exam's only 45 minutes. You're going to be looking at videos and stuff and not answering questions. So that's probably the way that they're going to design this, in order to prevent people from well, to mitigate the effects of any sort of cheating. Okay, so pause the video, try to answer these, and then come back when you are finished. All right, I hope you took the time to pause the video and do those. Otherwise, you're just going to be moving along and not understanding the information. So let's do the second thing. Now, I love the way they do this, because this is the way I actually do it in class. I combine Newton's first law and Newton's third law in that order. I save Newton's second law because that is the most complex one, so I save that on its own. And look at the order that the AP exam is suggesting that you do it. Well, if you noticed, I do dynamics first, because I think it's better to know the origination of velocity, displacement, and acceleration. It's from a force, so that's why I do dynamics first. But other than that, I do follow along exactly with what they were suggesting. So let's go into Newton's first law, a deceptively simple law. So there's an actual name for this one. It's called the law of inertia. And this would be his first law. Now, there's many ways to state this law, but I'm going to use my own little variation of it. You probably heard it a million different times. Normally, students learn this in middle school. So, an object at rest will remain at rest. And an object, and I'm just going to put, just repeating there, in motion will remain in motion. Unless acted upon by a net external force. All right, so you've probably heard some variation of this. We're going to cover this because it seems really, really simple, all right? So let's just cover the first one, which almost no students have problems with, all right? So an object at rest, and we're just going to draw our table, and we'll put a box on the table. An object at rest will remain at rest unless acted upon by a net external force, all right? So that means that force, so if we go like this, all right, we're going to have force gravity on this, and we're going to have some sort of normal force. So let's say it didn't have any friction. You can see, and this is the first time we're kind of going through this with the free body diagram, the length of these arrows are important. So these two arrows, one goes up and one goes down, so effectively they cancel each other out. So what does that leave us with? That leaves us with one force. So what I mean by a net external force means that the forces don't cancel out. So that is a net external force that would cause that box to change its state. So the state that it's in right now is at rest. So that net external force will cause it to be in motion. All right. Now let's take a look at another example. Let's say that, and let me label this force. This is an applied force. Okay. And let's label now, let's say that there's a force friction here. If there's force friction and both of those cancel each other out, then there is no net external force. Since those two cancel out, the net force in all directions is zero. So that means there would be no change in the state, and the state is at rest. All right, like I said, I mean, most students don't have a problem with that one. This is the one that tricks people. What it says is that an object in motion, so we're gonna draw the Earth right here, and I'm just faking the continent. All right, so that's the Earth. So we're gonna be in space. All right. So we're going to have an object in space, let's say a rocket ship. There we go. So if we have a rocket ship in space, and let's say that it doesn't have its boosters on or anything, and it's just moving. It's already moving. It'll continue to move. So on this diagram right here, I'm going to disregard the force gravity from the planet. All right. We're going to assume that it's far enough away that the force gravity isn't there. You're probably wondering then, why did I draw the Earth? Because I just wanted to show that this was in space. All right. So in space, there's no air resistance or anything. So if this was moving without any boosters, let's give it a speed. All right. So speed is in, let's just say 50 meters per second. All right. So let's say it's moving at 50 meters per second. It doesn't need any force on it to continue to move that way. Newton said if an object is already in motion, then it doesn't need a force to keep it in motion. And this is what tricks most of the students, is because this term right here is called constant velocity. And think about what that term means. Constant velocity means that the velocity doesn't change. All right? So the term constant velocity is an object in motion. Let's add to this too. The object is going to move in a straight path. So the natural motion of an object is in a straight path. Now, think of a satellite or the moon or something. Think about how it goes in a circular path. Something that goes in a circular path needs what? A net external force. Okay? So that covers constant velocity. So let's say that this rocket ship wants to speed up. Let's say it wants to speed up. Then what does it need? It needs a net external force. Now, what happens if it wants to slow down? What happens if it wants to slow down? It also needs a net external force. But what's the difference between those going to be? It's going to be the direction of the force, which is why it was very important to know that forces are vectors and they have direction. So let's take this rocket right here. If we want this to speed up, then our force, let's just say it's moving in, let's say it's moving in this direction right here. If we want this to speed up, then the force here has to push it in that direction, right? So it's already moving. That force has to be in the same direction as the velocity, and it'll speed up. Now some of you are saying, well, isn't that acceleration? It is acceleration, all right? Now let's take a look at the other example. So we have the rocket ship right here. It's still moving in that eastward direction, but now we want it to slow down. So where does the force have to go? The force has to go in the opposite direction, all right? So the force has to go in the opposite direction of the velocity. Therefore, it slows down. That is also acceleration. And I know what you're thinking. You're like, doesn't acceleration just mean speeding up? No, it means speeding up and slowing down because acceleration is a vector also. And we'll cover that a little bit later. All right. So now we've covered what a net force is. All right. And take a look at these. Look at this one right here. There's only one force on that object there. That means that's a net force. It has nothing to cancel it out. There's only one force on the object there. That means it's a net force. All right, it can't be zero. Now, what do I mean by external? Well, there's a really good experiment, and if you look it up on YouTube, you'll definitely find it, where they have an object that has wheels. And maybe you've done this experiment in class. And then they put some sort of fan on here. So I'm just going to make, that's a fan, all right? So when they turn that fan on, you can guess that if it blows this way, right? Then this cart will move in that direction. Pretty simple, right? Most people understand that. But then what they do is they attach a sail to it. They attach a sail right here. And they attach it to the frame of the object. And then, well, it's a rigid sail. And then what happens to the object? They do the same experiment. They turn the fan on, and then the object doesn't move. All right? In one case, it's an external. It creates an external force. And in the other case, it's an internal force because all of the components of that are attached to each other. Now, we're going to go over that a little bit more with the third law, because that's a perfect example to show the third law and where these forces are. Okay? Another thing, think about it. I'm going to draw my car. I don't think you could ever just look at these notes and see what's happening. You'd actually have to see the video. Sorry about that. That's the way my thinking is. Alright, so if we have a car and we want to push this car, everyone knows that the person would have to be outside that car in order to move it. There's no way that if you're inside the car, if you're inside and you're pushing on the dashboard, that that's going to move. All right? So, external force, internal force. All right? It's the same reason, like if you were sitting on a chair. Here's one more example. Let's just solidify this example right here. And it was on wheels. Yeah, it's not too bad of a chair. All right? If you were sitting on here and you pushed on your chest, right? You pushed on your chest. It wouldn't move this, all right? You need an external force. So you would have your you'd have your feet on the ground and then you could push off and create an external force. But there's no way you can move this by hitting on your own chest, all right? That would be an internal force and an external. All right, guys. One more thing. What is inertia? Inertia is a property that's dependent on mass. So it's a property. There is no formula for inertia. I know sometimes they ask for one, but the property it depends on is mass. So if you think about it, is a larger object harder to stop? Well, yes. A larger object has more mass, therefore it has more inertia. So to change its state of motion requires more energy, more force, stuff like that. All right. So inertia is a property dependent on mass. There is no formula. All right, let's scroll back. So that covers Newton's first law, which leads us directly into Newton's third law. And I'm trying to keep these videos around a half an hour. So Newton's third law. So the question I almost always get is, does it matter the order of these laws? And absolutely it does matter the order. Okay. The first one is the law of inertia. The second one is net force is equal to mass times acceleration. And the third law is the action-reaction. All right. So let's write this down. For every action, there is an equal and opposite reaction. Another deceptively simple definition. So I'm going to underline these right here. Because if you notice, there is an equal and opposite. Both of these must apply. So the first question, and I think this is pretty intuitive on the definition, but when we talk about an object, and this is the question that they almost always ask with this, well, then how does an object move? So if we have an object here, and we push with the force applied in this direction, then Newton's law said there must be an equal and opposite reaction. So people think that that is like this, all right? That's our reaction. So this would be the action, and this would be some sort of reaction. Now, if they're equal and opposite, then that object could obviously never move, right? Because equal and opposite. Now, here's the key to this. And I really don't, I've seen this so many times. I guess they just assume that people know this. The force is there we go. That was an important word, so I had to redo it. All right. The force is on separate objects. So Newton's third law is the interaction between two objects. You have to have two objects. Otherwise, you're going to draw the two forces that go equal opposite, and it's not going to make sense. All right. So let's cover a couple of examples. So let's say we have box A and we have box B. All right. These two are going to push into each other. So let's say they look like this originally. They look like this. So this is A and this is B, and they're being pushed from right here. So this is our applied force right here. Okay? So let's draw the free body diagram. And the free body diagram is the diagram of each separated. Now, it's going to be on a table, so I'm not going to draw force gravity and force normal because I don't want to confuse anybody. Okay? So let's draw this. So box A has a vector that looks like that. That's our applied force. All right. Now, box A is going to push into box B, so it's going to push that box in this direction, and we're going to label it force on B by A. So the way we label it is we do the object first, force on B by A. Now, Newton said that when two objects interact, there's an equal and opposite force on each one. So B is going to push back on A like this. And that's going to be force on A by B. Just like that. And what are our Newton's third law of forces? It's F, A, B must equal to F, B, comma, A. Now, in a problem, they might ask you, what is the net force on A? And now that you have a free body diagram, you can figure that out. They may ask you, what is the net force on B? And you can figure that out too, okay? Anyways, the free body diagram gets you to that point. So, force on A by B and force on B by A. Now, let's take a look at something. Let's take a look at a ball right here. A ball is falling to the ground. It has gravity on it, force gravity, and it also has air resistance. Air resistance, okay? Now, these two vectors are equal and opposite, so we're going to call this terminal velocity. That's what they call it. Terminal velocity is when an object meets the right amount of air resistance and it doesn't change its velocity anymore. It moves at constant velocity. Okay. Now, if these are equal and opposite, the question is, are they Newton's third law of forces? And I'm going to get a red pen for this because everyone should be saying, no, they aren't. And if I asked you, why are they not Newton's third law of forces, you would say because they're on the same object. And you would be correct. We're going to look at another example, our handy dandy book on a table. What forces are on there? Force gravity going down and force normal going up. Those are definitely equal and opposite because that book is sitting on the table, so it's not moving up or down. However, are they Newton's third law of forces? Of course not, because they are on the same object. But let's take that same thing. Let's take that same diagram. So we're going to have our table. We're going to have the book. We're going to have the ground, and I'm just going to make it squiggly so that you don't think, so you can tell it's a different thing. And then we're going to draw our book on here. Okay? Now, let's take a look at this. The book has force gravity going down. It also has a normal force going up. But what is the normal force created from? It's created from the table. So let's relabel the normal force as a Newton's third law force. So that force is actually force on book. So this time I'm actually going to use the objects by the table. Now let's look at the table, all right? The table has what on it? It has force gravity going down. I should have did this in a different color. Anyways, force gravity going down, okay? And then what else does it have? It also has force on table by the, you guessed it, by the book. So force on table by the book. So this force right here and this force right here are Newton's third law forces. Force normal and force gravity right here are not. Force on book by table and force on table by book are equal and opposite. And guess what? They're on two different objects. One's on the book, one's on the table. All right. Force gravity. So we have the table on the ground. So I'm going to say this is the ground right here. So we have the table exerting force on ground by the table. All right? And then on the table, we would have a force on the table by the ground. And I'm just going to put, oh, I better put Ground. I just was thinking someone might think that's gravity. Okay? So we have force on ground by table and force on table by the ground. Those are Newton's third law of forces. Finally, force gravity. And I'm not going to add that to this. Let's go back to the ball. All right. And this is an interesting thing because we have the Earth. And this one's a little bit harder to understand. And we have a ball that's falling to the Earth. So this force right here is force on ball by the Earth. All right, so that force is transferred through force gravity. But according to our law, there's an equal and opposite reaction. So there's actually a force like this that goes up. And this is force on the Earth by the ball. This force is transmitted through that gravity interaction. All right. So you have the ball being pulled down by the Earth, and you have the Earth being pulled up by the ball through force gravity. And these are Newton's third law of forces. Okay. One more example that is very common with Newton's third law. All right, the tug of war. So we have person A, and we have person B. All right, and we have a rope. They're doing tug of war right here. So person A is pulling in this direction, and person B is pulling in this direction. We're going to say the rope is negligible in this. It's just a conduit for the two forces. All right. So according to Newton's third law, right? So we have this one. We have on person B, we have a force going. I am going to use a different color because it's starting to look. According to Newton's third law, we have a force going in this direction. This would be force on person B by A. And then we have a force going in this direction right here, and this would be force on person A by B. These are equal and opposite because they're on different people. So those qualify as Newton's third law of forces. So if that's all that we drew right here, you could see that there would be no movement in tug of war. But what you're forgetting about is that this person right here also has an interaction with the ground. All right. So when they push on the ground this way, so this would be force on the ground by person A. Then what's going to happen to the ground? The ground's going to exert a force on the person in this direction right here. So force on person by the ground. Okay? Now, this person over here, right here, they're also going to have that. So they're going to push in this direction. So they're going to push in this direction right here. So this is force on the ground by person B. And of course, what's going to happen here? Force on person by the ground. So what is the situation where there'd be no movement if A and B were both pushing on the ground with the same amount of force? They would still be in a stalemate. However, think about A being stronger than B. So A is going to push on the ground more, which is going to create a larger force on the person, right? Which creates a net force going in the leftward direction, and that means the whole thing would move to the left. All right. You could also say B. If B was stronger, B would push to the left more, creating a larger force to the right, which would be a larger net force than what's on person A, and would move to the right. Okay. So when they talk about Newton's third law, they often ask this question. All right, we're going to cover once again the car, and everyone should recognize by now this is a car. And we're going to have a little bug here. So the bug's going to be moving in this direction, and the car will be moving in this direction. And the question is going to be, what are the forces exerted by each of the objects going to be in relationship to each other? And of course, you're going to answer this. They are equal and opposite. Now I know the thinking here is, well, the car has a much larger mass. So doesn't that mean the force is going to be a lot greater and than the bug, which has a smaller mass? But Newton didn't say that. He said that when two objects interact with each other, nothing to do with the mass, they exert an equal and opposite force. We'll cover what actually happens because something has to happen in this. But in this case, this is a very popular question. Another thing is a rope. And we have a person that is climbing that rope. All right. So what is the person going to do? The person is obviously going to pull down on the rope. So we're going to draw this, and we're going to put force on rope by the person. Now, there's an equal and opposite reaction, and it's on a separate object. So guess what the person's going to feel? The person is going to have the force on the person by the rope. And if you look here, those two are going to cancel each other out. But we have another force on that person. We have force gravity going down. So let's say that force gravity, let's say that this person weighs, and I'm just going to make a, let's say 50 newtons. All right? So in order for, well, let's just say the person pulls down on the rope with 50 newtons. That means that the person, the force on the person by the rope is also 50 newtons. Well, what's going to happen here? It's 50 newtons and 50 newtons. Those two cancel each other out. The person wouldn't move on the rope. So how does the person move on the rope? They pull down harder. So let's say the person pulls down with 60 newtons of force. Now, what does the rope pull up at? 60 newtons. And now look what you have. You have a net force because 60 minus the 50 gives you 10 newtons of net force, and that person would move up the rope. All right. Finally, our little windmill example. So we have some sort of cart that is on a track, and I'm going to draw this a little bit differently than before. I'm going to draw it like this. And what we're going to have is we're going to have this blowing in this direction right here. So the wind is going to blow out in this direction, right? Just like that. All right. So if the wind blows out in this direction, then we can imagine that this cart is going to move in this direction. So let's start drawing. And we're going to say that this whole thing is a system, all right? The fan is attached to the cart and the wheels and stuff, okay? So let's draw some of the things. We know that this has force gravity, and we know that this has force normal. those two are going to cancel each other out. So those don't have anything to do with net force. Okay? So let's figure out where this force over here is coming from. Where is this force coming from? All right, so we have the airflow going to the right. So what is that? There's actually another object there. It's the air molecules. All right, the air molecules are being forced through there. So this would be force on the air by the fan. And guess what's going to happen? The air is going to do an equal and opposite reaction. So this is going to be the force on the fan by the air. Makes sense, right? Since that force right there is on the cart, that's the force that creates the movement. That's the net force. Okay, so what's the difference when we add a sail? When we add a sail here, okay? So we already said that we have force on the air by the fan, all right? However, in this case, what's going to happen here? That force on the air by the fan is now going to hit this little sail. So let's call this a sail. So that's going to create something that looks like this right here. So this will be force on the sail by the air. Now, we know what's going to happen, right? The sail is going to do an equal and opposite reaction, and it's going to go in the opposite direction. So it's going to create this on the air. Force on the air by the sail. All right? Now, if we take a look at this right here, and we take a look at this right here, these actually are opposite. All right? Are they Newton's third law forces? No, because the blue ones are third law forces and the red ones are third law forces. But the blue and the red have the same magnitude. They have the same arrow length in opposite directions. So those two cancel each other out. And guess what those both are connected to? They're connected to the cart. So through Newton's third law, you can see why the cart does not move. All right, I think that covers everything. So we covered Newton's third law. All right, next video will be Newton's second law and application of that. And you probably have noticed we haven't used much math yet. I think a lot of people think physics is just math, but the fundamental concepts are integral to using that math. So we've set up our base theories and logic in order to understand what's going on, and then we're going to use math to prove it, definitely in the second law. All right, thanks a lot. I guess it wouldn't make sense if I didn't give you the answers to these, since I don't know if you have a way of checking it otherwise. So let's give you some of the answers. All right, draw a free body diagram of a car rolling down a hill, speeding up with friction. So you should have some sort of this, something like this. There's my car. So I'm going to have force gravity. Then if it's speeding up, that's because of force gravity. Then I'm going to have force normal. I guess since I didn't say anything, you could have put something here like the force of the engine. And then something here that says force friction. I know we didn't really go into it, but arrow lengths would definitely be uh, useful. The force of the engine would have to be larger than the force of the friction. You could have also done it without the force of the engine and just left it empty like that, saying that force gravity is responsible for it rolling down the hill. All right, what does the statement forces are vectors mean? So that means that they have magnitude and they have direction. And how do I represent these? With some sort of arrow. Some sort of arrow. So that's the answer. What is the difference between mass and weight? Mass is always constant. It's the same everywhere. Weight depends on gravity, g, the acceleration due to gravity. What were the two types of system called? We had an inclined plane, I'm just going to abbreviate, and Atwood machine. What effect does the Earth have? Well, the Earth is actually force, gravity, which is also called weight. And kudos if you also got mass times gravity. Describe one impossibility for each system and explain why. You could have done basically anything in here, anything that didn't make sense. The one I would have said is if this was a ball and it was a wooden ramp, there's no way that that ball could slow down because that ramp is a wooden ramp and the friction on there isn't enough for it to slow down. So I would say that would be an impossibility in real life. All right. So the one field force that we had was force gravity. And then all the contact forces. So let's see, we had force applied. We had force of friction. We had tension, which is transmitted through ropes. And we had the normal force, which is perpendicular to a surface. And all forces have the same unit, which is a Newton, which is a kilogram times the acceleration, which is meters per second squared. Those are the SI units. And it doesn't matter which one we're talking about, whether it's weight, applied force, frictional force, tension force, or normal force. They are all measured in newtons based off of Isaac Newton. All right, those are all your answers.